Hello students, and welcome to this module about district heating, district cooling and electricity production and combinations thereof. This is the third technical module, and what we will talk about today is briefly introduction to the cold water production. What you will learn in this module is a little bit about the temperature levels and about absorption heat pumps, and we will also talk little bit about what is the general idea. Now, to be able to follow this module, you must be fully comfortable with the functionality of compressor heat pumps. Absorption heat pumps are a bit more complicated, and we will go through that now. But so compressor heat pumps was one major issue in the previous module. As a preparation, I will want you to read 4 pages in chapter 2, pages 19 to 23 in the IRENA roadmap report. And you will find that these pages also include a little bit about policies and how to make these systems come into place. So pause the recording now and then read those pages. So, welcome back. You may have noticed while reading that in countries where electricity prices are low can electrical chillers be used, while in other countries may fuel be used. And you can use industrial surplus heat to produce cooling. The key to several of these solutions is the use of absorption heat pumps, usually not compressor heat pumps. But in some cases you would use compressor heat pumps driven by a gas engine. The choice between an electrically driven compressor heat pump and a gas-driven will mainly depend on the ratio of electricity price to gas price. Now it becomes extremely important that you understand the working principle of the absorption heat pump. What I've done in this slide is to collect 3 simple descriptions of the absorption heat pump. Altogether, they are less than 20 minutes, but I'd say they give you all the basics. So regard this as an absorption heat pump crash course. When you have looked at these 3 videos, you will understand why the absorption heat pump using lithium bromide in water is such an excellent candidate to use in the combination with district heating systems. And you will understand why it fits together with electricity production. The thing with district cooling is that the distributed heat sink has a temperature that is well below 10 degrees Celsius. And it's no problem to work at lower temperatures down to say 4 degrees. To produce this low temperature, will the heat pump need a high temperature energy source. And that high temperature source should preferably be in the district heating temperature range. And that is exactly what it is when lithium bromide and water are used inside the pump. The point with this combination is that the water is used as the refrigerant. Since you will most often want to co-produce and sell electricity, you do not want to have a very electricity demanding process in the plant. You want to sell the electricity, not use it internally in the processes. And the absorption heat pump demands very little electricity. The price paid for these advantages is that the COP is less than unity. So if you want to cool away 1 megajoule of surplus heat from a customer, you will have to input maybe 1.5 megajoules of district heat into the heat pump. And then you have to vent away 2.5 megajoules of energy from the plant. So it becomes a question of a low-cost production of the district heat, and then of how much your customers are willing to pay for their comfort cooling. Heat pumps are not the only option to offer cooling services to the customers. But before we bring up other methods, I will want you to download some material on heat pumps to get yourself a quantitative idea of what can be achieved. So log in at the home page of the Italian Association of Chemical Engineers and then go on to their journal and find volume 81 of 2020 and then search for the word refrigeration and then just download that paper. The paper is only 6 pages, so read it. The most important thing in that paper are the results. What is clear from the results is that to arrive at a COP exceeding 0.7, you will need to use a hot source temperature of at least 103 degrees. Now, I cannot know how familiar you are with the thermodynamics of steam turbines. We will touch upon that briefly in the next module. But for the moment, I'd like you just to accept that the higher the hot source temperature for the heat pump, the less electricity can be produced. And that is because the hot source temperature is basically the exit temperature from the steam turbine. So, a COP of 0.7 means that to offer a 1 megajoule cooling service to the customers, the heat pump must be supplied with more than 1.4 megajoules of heat. If the heat pump was working at a COP of 0.5, we would have to supply it with 2 megajoules to arrive at the same cooling capacity. And at a COP of 0.33, we'd have to supply 3 megajoules. But then we would be able to produce more electricity. So we will have to compromise. But the absorption heat pumps gives a system with a fair amount of flexibility. Now look at the last 4 minutes of the second video in the absorption heat pump crash course, from slide number 4 in this presentation. That is a case study, a Sankey diagram showing how the combination of district heating, cooling and electricity production looks in a real case. What you will realize is that offering a cooling service to customers using an absorption heat pump is radically different from the delivery of heating and electricity. While heat and electricity are plant outputs, will the cooling become a plant input? So it shows up completely different in the plant energy balance. Let's now have a brief look at some other options. Beside heat pumps, there is one major option, and that is free cooling. Just as there may, in some places, be heat available for free from geothermal wells, may there be cold water available for free. The slide indicates how free cooling can be arranged. Of course, this is only a schematic, and I have just set some reasonable values for the temperatures. But with a counter current heat exchanger, this would be quite reasonable. As it comes to the preparation of the water in the closed loop, just as for heating is the coolant water enclosed, will there be demands on hardness, on pH, on salt contents, on particles, and on the oxygen level? Basically, will the demands be the same for the district cooling water as they were for the district heating water? But since temperatures in this case are lower, will of course all chemical processes, like corrosion, be much slower. But they will still be there. You might also use solar heaters and combine that with an absorption heat pump. Centrifugal compressor chillers are also quite common. Basically, you compress a gas using a centrifugal compressor, and then you cool the high-pressure gas to a cold, high-pressure condensate, or maybe it's still a gas but at a low temperature. And then you lower the pressure and allow the condensate or the compressed cold gas to flash that is to evaporate or to expand into a low pressure chamber. The energy uptake during the evaporation or the expansion is used to cool the coolant, and then the gas is compressed again. This is quite a common type of system. In the very small scale, like single houses, may Peltier cells find use, but that is not very common. If you have access to cheap gas or oil, may a compressor heat pump utilizing a gas or oil-fueled engine be an alternative? So there are several options. Now you should read section 2.3 through 3.3, starting on page 23 and ending on page 40 in the IRENA Roadmap report. There are a number of case studies and there are a number of technology examples, and what you should do is to see to that you understand fully the implications and that you understand fully the way to think and prepare when you want to consider a new installation. Put special emphasis also on figures 10 and 11, in which are shown some rough cost breakdowns for different types of systems. I personally think that sections 3.4, 3.5 and 3.6 do not add so much, so I would suggest you just scan these sections. But on page 50 starts chapter 4, and that should be studied carefully. It's only 2 pages. Just scan the first part of chapter 5, but read section 5.2 and the conclusions in chapter 6, pages 60 through 64 carefully. As for the annexes, is Annex 1, pages 78 through 81, concentrated on the methods used to make the report. You may perhaps want to look at how the cost estimates are done on pages 78 to 79. If you are interested, there is a more detailed description and breakdown of costs in Annex 5. But I want to warn you that cost estimates expressed in money are always guesswork. You will have to assume future interest rates, inflation, employment rates, international trade and tariffs, taxes, environmental fees and lots of other factors. So a cost comparison expressed in money may, at the very, very best, be valid at the moment it is done. The cost for an energy system should be evaluated in terms of thermodynamics. Energy or exergy cost-benefit analysis is relevant and can be evaluated to make a meaningful comparison. Money cannot, because such a comparison will always be time and place dependent. Annex 2, pages 82 and 83 deals with technical aspects, and you may want to look at that and compare some values to what you learned in the first module in this lesson. So this then ends the presentation in this module. Do the reading before you start on the next module.